This is what? Lecture 45. And I'm cold. It should not be this cold in May. So last class was huge. We did Green's theorem. Super, super exciting. And so, do you guys have any questions about any of those problems? I don't know if you do or don't. Homework, maybe. Going once, going twice. Oh, there's only 3 of us right now. This is so cute. Where's everybody else at? Okay, cool. So if you don't have questions, then what we do is we think like a mathematician or a scientist would. And we ask questions like, okay, well, actually, let's write Green's theorem down. It can never hurt to write things down and see them over and over again. Let's write it in a couple different forms, just so we recognize that there's a few ways to do it. First and foremost, we can write it like this. We can say that the line integral around some closed curve that's sufficiently nice. I like to write my line integrals like this. This is just the O'Grady way I like doing it. So under the hypotheses we talked about, this is a double integral. You take the second component's partial with respect to y, and you subtract the first component's partial with respect, g sub x minus f sub y dA. Or some people like to write it a little more, I guess this is non-vector language, I don't know. Maybe a classical way of doing it. These mean the same thing. 2 ways to write the same thing. And so don't forget what's very important about this. So let's get our guys out. So if we have some, remember, C has to be some closed curve. And it has to be oriented in the proper direction. And we said the convention is we imagine an object moving around in a counterclockwise way. So if this is D, this is our domain, and then C is the curve. So let's shade this in so we're all aware. We're integrating this region. So this is a very, very, very useful theorem. It relates a line integral to a double integral. And as I've mentioned, it has numerous applications. And what we mean by that is that we can interpret these integrals in many different ways. We talked about how these line integrals can be used to determine work done and to study things like flux and circulation. And there's, the applications are in many ways endless. So, cool fact, food for thought is what we would say. So, fact, Green's theorem, like the fundamental theorem of line integrals, are what we call generalizations of the FTC. the regular fundamental theorem of calculus that we learned way back in Calc 1 and we use all the time to evaluate integrals. And so the mathematician in us might say, okay, are there other generalizations? And of course there are going to be, or I wouldn't even pose this question. But we need more tools first. So when I say generalizations, let's think about the big picture. I think 2 classes ago, I tried to emphasize this big picture. How did I try to emphasize it? Well, I said we're relating the integral of over a region in terms of something on its boundary. So that's exactly what we did. That's what Green's theorem does. We say the integral over this D is related to some sort of property of the boundary of D. And that property of the boundary D happens to be an integral on that curve. And so in order to do that, other generalizations, like in higher dimensions, we need to make some new definitions. We need new tools. So we start with 2 types of derivatives. So I'm putting derivatives in quotations, but that's essentially what these things are. So to do this, we need to get some advanced, we need to start being sort of more advanced with our language. It's the best way to do this. So to do this, we start by defining a new vector called del. So what is del? It's this. Del is equal to, and by the way, I'm going to put this vector in quotations because what is it? Del is really, look at its first component. It's an operation. Its second component is an operation. And its third component is an operation. This might almost look to you like it's a gradient, but there's not. Notice there's no function here. So this is called an operator. Why is it called an operator? Because it operates on functions. It does something to them. So you've seen this symbol before. So, for example, I shouldn't say we use it. We can use this to define the gradient of a scalar. And what do we mean by that? Well, you guys know that. We just take the partial of f with respect to x, y, and z and throw it into a vector. But here's something it can also do. It can also be used to operate on vector fields. We know what a vector field is. A vector field is a function from, say, 2 dimensions to 2 dimensions, or 3 dimensions to 3 dimensions. And so in that sense, it's not scalar multiplication, but it's a dot product. So we could say, okay, the partial with respect to x, comma, the partial with respect to y, comma, the partial with respect to z, dotted with, what's f? Well, f, we give it components, maybe little f, little g, little h. And so what this becomes is it becomes the partial of f with respect to x plus the partial of g with respect to y plus the partial of h with respect to z. So let me be very clear here. This is the dot product. Does anybody have a question so far? So this thing above has physical meaning and is actually very important. So we're going to give it a name. We call the del dot f the divergence of the vector field. So this name, if you think about what this derivative does, if you draw pictures and play around, you'll see that this has some physical meaning to it. And oftentimes, as I said, when you're trying to associate physical meaning with vector fields and derivatives, it's often useful to think about things moving, maybe like an electric field or fluids flowing. So we can also compute the cross product. And we call this the curl of the vector field. So you might, you know, you could suffer through the calculation if you want, but just just to remind you what this is a vector, and it's the partial of h with respect to y minus partial of g with respect to z, comma, partial of f with respect to z minus partial of h with respect to x. Remember, to compute this, you have to use those determinants. But what you should do is test it, work it out yourself. But what I'd like to really draw your attention to is the third component of this. That looks like something we just saw with Green's theorem, and that is not a coincidence. So one of the things that the curl does, and the reason we call it the curl, is because it helps measure and quantify rotations. So again, think fluids. Think of a particle moving through a magnetic field or an electric field. I mean, again, there's lots of physical things you might ponder and think about how these mathematical things could help describe them. Does anybody have a question? Going once, going twice. Now, there's lots of things we could do. We could give you vector fields and stuff and say compute this stuff, and you should practice with that. Absolutely. By the way, I've mentioned to you guys before, when you Google things like Maxwell's equations or Ampere's law, things like electric potential, all these things that show up in physics and engineering, when you start looking at these equations, you're going to see these symbols. When you talk about things like angular speed, you're going to see these things. So, we're not just studying these things for the sake of that it's math, but we're also studying it because of the applications that they have. Anybody have a question? Okay. Are we having fun? I wonder. Are we having fun? I need some water. So let's do an example. So let's take something like f is, I don't know, how about 3xy, comma, 5y squared, 6 e to the z. So let's compute the divergence. And by the way, sometimes we write divergence of f. We actually spell it out. But it's this dot f. So let's do these very carefully in the beginning. And I would advise that you do the same until you get very good at it. So when you dot this, you're taking the partial of the first component with respect to x, so you get 3y. Then you're taking the second component with respect to y, so you get 10y. And then the last with respect to z, so you just get 6e to the z. And of course, we can clean this up as 13y plus 6e to the z. Any questions or comments about the divergence? I wonder if I can copy this. I never tried this. Oh, I guess not. Oh well. Control copy works. Nope. Oh well. All right, so let's do the curl of this creature now. So let's just so we don't have to keep flipping back, let's write it back down again. What was it? 3xy, and then it was 5y squared, I think. 3xy, 5y squared, and then 6e to the z. So this will be good practice with the curl, because the curl will give us good practice with the cross product. So remember what this creature is. How do you take this? You have your I, your j, and your k. Then you have your del vector, which is the partial with respect to x, partial with respect to y, partial with respect to z, and then what's your f? So you might have to get in your time machine and go back to when we were able to sort of check out how to do these. So does anybody have a question right now about how I set this up? All right, so what are we going to do? You cover up the first row and the first column, and you take that determinant. And what's going to happen is, so I have I times, well, this guy doesn't have a y in it, so I get 0. And this guy doesn't have a y in it, or z in it, so I get 0. And then I have minus j, and then I have a 0, minus a 0. And then lastly, I have my plus k. And the partial with respect to y is just 3x. And then the partial of this guy with respect to x is 0. So when I clean this up, I get 0, 0, 3x. So this is a calculation you might want to spend some time on. making sure you get it. Computing curls, as you can see, is a very tedious task. Do, 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 do. Do, 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 do. Okay, so let's do one more example here. So let's take the following. Let's take f of x. So now I'm going to give you a scalar function. Let's say e to the x sine y plus 4z squared. Let's compute the following. Gradient, or excuse me, del dotted with the gradient of f. So if I take the partial of this thing with respect to x, I get e to the x sine of y. If I take it with respect to y, I get e to the x cosine y. And then if I take the partial with respect to z, I get 8z. Now I'm going to take the partial of respect x, y, and z, put them in the vector, that's my del operator, and I'm going to dot it with this creature. And so when I do that, I get e to the x sine y minus e to the x sine y plus 8. And so, of course, this thing adds all the way up to 8. Does anybody have a question about that calculation? So what we just did is actually one of the more important computations in many areas of physics and engineering. So the operator, which was this, dotted with this, is so important. It has a name. It's called the Laplacian. And if you actually worked out what we just did in general, the Laplacian of f, which is the gradient, or excuse me, the del operator dotted with the gradient of f, so you do it twice. If you walk through that, you actually get the following. You get the partial with respect to x, and then the partial with respect to x, and then you add that to the second order partial with y, and the second order partial with z. Woo! So we use this triangle to represent that this is the Laplacian. And by the way, if you just Google things like heat equation and wave equation, these equations that are, you know, the fundamental equations of certain areas of engineering and physics, you'll see this guy pop up everywhere. Does anybody have a question? Okay, does anybody have a question, comment? All right, I guess this is a good place to stop. What I would encourage you do is you practice some of these. Just pick random functions, differentiate them, find their divergence, find their curl. Because we're going to be needing to know how to do this in what comes. So don't forget, we have a goal. Our goal is to get these integral formulas generalized to higher dimensions. And in order to do that, we have to be able to compute these new things, these divergences and these curls. So what we'll do on Monday is we'll talk about a new type of integral we haven't done yet. It's called a surface integral. So we're going to integrate over the surface of something. You want to know the average temperature on the surface of the Earth? You need to integrate a surface. So we're going to get to that on Monday, and then we're going to use our knowledge of, well, not our knowledge, then we're going to derive some useful identities. So, and that's it. So we'll have class next Monday and Wednesday, and maybe, well, we can always meet Friday if you want. Does anybody have any questions? Don't forget, I'm going to give you your exam probably Monday or Tuesday at the latest, and then you'll have a week to do it. Okay?
Yeah, I have a quick question. I missed the first half of this because of a computer issue. When do you upload these videos?
They're on YouTube. Or when or when? Why? Or wait, when?
When? No, why?
Well, I'll actually, no, I know. I'll try to, I'll probably upload it literally. So once I'm done with this, it takes about 20 minutes for it to compress. Maybe not 20 minutes, maybe like 5 or 10 minutes, I'm lying. And then once it compresses and saves to my computer, then I upload it to YouTube. I have no idea how long it takes them to do it. It takes me about 10 minutes to do everything. And then however long before YouTube makes it viewable. So maybe 5 minutes, maybe an hour, I don't know. I think it depends on however busy the YouTube servers are at any given time. You know? All you missed, though, by the way, it's worth checking out. maybe since this is a shorter video too, it's only like a half an hour. It won't take as long. Make sense?
Sounds good, man. Thank you.
All right, no problem. Thank you guys. All right, well, listen, I'm going to end this then. I will post, like I said, I'll upload to YouTube right now. Hopefully it takes just a few minutes. And you guys have a good weekend. I hope to see you Monday. If you have any questions, just email me. All right? All right. See you guys. Be safe.